Continuing on with section 5.3, I want to talk about transformations of graphs. So let's go with 2 pi, pi over 2, 3 pi over 2, 1, negative 1. And we'll get a rough sketch of the sine graph there. Now, once you've got the basic shape of the sine graph, there's a number of different transformations that we can take. For example, if this one here, y equals sine of t, well, suppose I wanted to do y equals sine of t minus 1. Well, all that's really going to do is shift the graph down by 1. So, put a spot there at negative 2. So here, I'm at 1, I'm at 0. I'm going to get moved down to negative 1. Here I'm at positive 1. I'm going to get moved down to 0. Similarly, down to negative 1, down to negative 2, back to negative 1. And you'll notice that the same basic shape is going to be included. I could do something similar if I wanted to do y equals sine of t plus 1. I think you can see from the dots what I'm working with here. We've got that same thing. So we can kind of shift the graphs of sine. We can do the same sort of thing with cosine. I believe the examples in your book tend to deal with cosine, but we can shift it up and down. Now there's a few other things that we can modify. And the first one that I want to talk about is amplitude. So if I have y equals sine of t, the amplitude of that graph is going to be 1. As we see here, the amplitude's 1 because the distance from the axis to the peak is 1. From the axis to the trough is 1. So the maximum distance I can get away from the x-axis for this graph is 1. Now the amplitude can be modified if I was to multiply sine by a different value. So suppose I went with y equals 2 sine t. Let's get rid of that there, we'll need a little bit more room. The amplitude then should be 2. I'm taking every value for a given input and multiplying it by 2. So when I multiply 0 by 2, I still get 0. So that point and that point shouldn't move. But at pi over 2 and at 3 pi over 2, previously I was up here at 1, I'm going to multiply by 2. It's going to take me up to positive 2. Similarly, down here at negative 1, I multiply by 2. Takes me down to negative 2. And so now I get this shape. Same basic graph, but I've stretched it. Now something else that's kind of interesting, suppose I had y equals negative 2 sine t. This graph and this graph will both have amplitude of 2, but this negative sign here is going to flip the sine graph upside down, because at 0, I'm still at 0, multiplying 0 by negative 2 doesn't do anything, but here I was at positive 1. When I multiply it by negative 2, it moves that point down here. And over here I was at negative 1, multiplying it by negative 2, it's going to move me up here. And the same basic shape, the same periodic structure still holds. and we get something like that. So we're always going to be building off this sine curve. It's just a matter of how I can stretch it or flip it when I'm changing the amplitude. Another thing I can change is the period. Now, if y was equal to sine of t, we've talked about this a lot, we've seen it in all the graphs, the period is 2 pi. So, put 1 up here, negative 1 down here. Everything repeats every 2 pi. But what if I wanted to try to graph sine of 2t? Now, the amplitude should be the same, because I don't have any coefficient in here to mess this up. But now, when I plug in a value for t, I need to double it before I get the value. So previously, if we look at pi over 2, 3 pi over 2, when I used pi over 2 as an input, I get an output of 1. But if I look at this function in blue, plug in 0 for t, I still get 0. But when I plug in pi over 2, 2 times pi over 2 is pi. And what's the sign of pi? Well, it's 0. If I plugged in pi as my input, 2 times pi is 2 pi, the sign of 2 pi is 0. Well, what's happening in between? I need to look at a few other points. Pi over 4, 3 pi over 4. If I take pi over 4 and double it, I get pi over 2. 2 times pi over 4 is pi over 2, and sine of pi over 2 we know is 1. Similarly, 2 times 3 pi over 4 is 3 pi over 2. We know the sine of 3 pi over 2 is negative 1. So I end up down here. And so the period, previously, we started with a period of 2 pi, but after multiplying, we're left with a period of pi. We were able to shorten the period by multiplying the variable by a coefficient. Now, in general, sine of k times t has period 2 pi over k. So you see some examples of this in your text. If k is a nice positive number, like 2, it took 2 pi and it shortened it. If k was a fraction, like a half or a third, it would lengthen the period out. So we've shifted the sine curve up and down, we've stretched it vertically, we've shrunk it horizontally. The other thing we want to look at is what's called a phase shift. And that's going to be what happens if I shift the curve to the left or right horizontally. So again, there we go. Pi, 2 pi, 1 or negative 1, as per the usual. So in red I've got y equals sine of t. And then in blue, let's go with y equals sine of t minus 2 pi. Well, I guess I don't want to quite go there. That's not going to make it too interesting. Let's do t minus pi over 2. So I better put my pi over 2's on here. Pi over 2, 3 pi over 2. I'll even stick another 5 pi over 2 out there. And now I look at what's going to happen. I know that normally if I take sine of pi over 2, I get 0, or sine of 0, I should get 0. But if I take pi over 2 and plug that in for t, pi over 2 minus pi over 2 would be 0. So when I get pi over 2, I get the same thing that I would have gotten with 0. What I've done here is called a phase shift. I have shifted everything to the right by pi over 2. So I'm going to get a point up here, a point here, a point here, a point here. This is why I had to go up to 5 pi over 2. Connect the dot there. Pretend I can draw. So I was able to shift horizontally by adding or subtracting some value from t here. So putting it all together, if I'm left with y equals, let's go with a times the sine of k times t minus b. If you're asked to sketch this, and again your book goes through this in a fair bit of detail, your amplitude is going to be a. So whatever this coefficient is, if it's 1, you're just got an amplitude of 1. If it's a half, the amplitude's a half. If it's 7, your amplitude is 7. We're going to have the period pi divided by k. And again, if k is larger than 1, this is going to shrink your graph horizontally. If k is between 0 and 1, if k is a small fraction, this is going to stretch it out. And we've got a phase shift of b. And if you've got this phase shift, b plus 2 pi is going to be what one period of your graph is going to look like. One period of the graph is going to exist on this interval, and so that's where you're going to want to get the sketch. So take a look at the examples in the second half of section 5.3. We'll move on to section 5.4 next, and some of the graphs of the other trig functions.